Welcome to Karolina Asks the Universe podcast. Hello everyone, welcome to our weekly podcast Karolina Asks the Universe, and today I have another amazing guest, another friend of mine at Harvard, Beatrice Kulterer. I hope I pronounce it correctly. If not, you can correct me. And today we're going to talk about molecules in interstellar medium, and also you might be surprised, but we found some alcohol in space. It's not only the one that we are drinking, but also there is some alcohol in space. But before we touch that, I would love to ask you about your PhD. So how did your scientific journey started? So where did you do it, and how was it? What is it about?
Okay, so I did my PhD in Europe, in Bern, in Switzerland, at the Center for Space and Habitability. And I did my degree in astrochemistry. So initially I started to study astronomy and earth sciences during undergrad in Vienna, but I was always interested in how to combine those two disciplines together. So astrochemistry, when I got the opportunity, seemed like a good option for that. And yeah, I had the luck to have a 4-year PhD position in Switzerland, which gave me a bit more time to do some research.
So Switzerland usually has 3?
Switzerland usually has 4, but if I would have stayed in Austria, I would have only had 3.
Okay, I see.
Yeah.
Yeah, 4 is. I feel like 4 is more reasonable for a PhD.
Yeah.
Okay, and what was your PhD project about?
The idea was to trace molecules in space across different stages of star formation. So before we have like a system like our solar system of planets, everything starts in just like a cloud of gas and dust, which we refer to as a molecular cloud. And at some points, enough material accumulates at the center of such a molecular cloud, where the temperatures go down and the density goes up, that it becomes unstable. And it collapses and starts to form a protostar, so a star that is still accreting mass from its surrounding.
So it's like a protostar, so like a baby star.
Exactly, like a baby star that still has to gather its mass. And there's still a lot of this natal gas and dust around it that feeds onto the star. And at some point, a part of that material has dissipated, and you are left with what we call a protoplanetary disk, which is the location where we start to form planets. And we see molecules in those molecular clouds. We see molecules around protostars, and we see molecules in protoplanetary disks. So I have always been interested in how do these different stages connect, how much of that initial material survives that whole process, because those molecular clouds are super cold, like they have temperatures of 10 Kelvin, so just 10 degrees above the absolute 0 point. But around protostars, the material can get heated up to hundreds and thousands of Kelvin, so there's like a lot of chemistry can happen, and things get destroyed and reprocessed. And if we study molecules across different stages of star formation, because we find the same across those stages, but we don't know how they are connected. So I've been studying their evolution.
So you're basically were studying, still, because you're working on a similar topic, interstellar medium, in a sense, like what are the materia between the stars, right? Like what's going on there, especially in the moment of star forming.
Yeah.
Okay, so you're saying while star is forming, there is like a lot of heat and different conditions that can create weird molecules that we were surprised to find.
Yeah.
Great. When was the time we found this weird molecule? When did this started, this astrochemistry and astronomy, this astrochemistry field? Where do you know when this first molecules were?
So the first molecule was already found at the end of the 1930s, which was, just a small diatomic molecule. But ever since, especially the past 25 years, the number of molecules have increased that we find. So as of today, we have detected over 350 molecules in interstellar space. And this is mainly thanks to radio astronomy and radio telescopes.
I was about to ask you, which telescopes are mostly responsible for that?
So radio telescopes, so for instance, single dish antennas, where you have just one big telescope with... There's, for instance, the RM telescope in Spain, which has a diameter of 30 meters, or the Green Bank telescope in West Virginia in the States.
The thing with radio telescopes is that they're a little bit easier to build, because the dish, it doesn't have to be made, doesn't have to be that even as because we are looking at different wavelength. And that's why it's easier to build a bigger telescope. So as you said, 30 meter is not, it's still big radio telescope, but it's easier to build that. That's why we have
Yeah.
them.
Yeah.
And another telescopes, also do you use ALMA?
Yes, ALMA is also a fantastic telescope, and it actually consists of multiple antennas that can be combined into one big telescope. And you can move the distances between the 40 antennas, so you will be able to look at different spatial resolutions in space depending on how the telescopes are positioned. And another telescope that I've been using a lot, which is actually like local to the institute here, is the submillimeter array in Hawaii. So there are 8 antennas on top of Mauna Kea in Hawaii.
Great. How big are these antennas? I don't remember.
The SMA antennas are 7 meters.
So 6,
8.
8, 7-meter antennas in Hawaii.
Yeah.
Amazing. So moving on to the things you're working on right now. So are you more like an observer, or you just like you apply for time on these telescopes and get this data and analyze that?
Yeah, this is what I've been mainly up to the past 2 years. 6 so far.
6 so far.
Yeah.
6 bigger telescopes you got time on. That's amazing. So each time you have to you had to write your own like small proposal in order to get the time on these bigger telescopes.
Exactly.
And you've been successful 6 times. That's impressive. Congratulations. And tell me, what do you do with this data? So you're observing in radio. We have something. How does data look like, and like?
So basically what we get from the telescope is raw data that still has to be processed. So there, depending on the telescope, there's different steps to do the data calibration. So if you just have one single antenna, it is a lot easier. If you're using ALMA or the SMA, you still have to combine the data from all of the antennas. And then also, depending on where the telescope is located and what frequency, so what parts of the electromagnetic spectrum you look at, the calibration process might be more difficult or easier. Because, for instance, when we observe from Earth, we unfortunately have to look through Earth's atmosphere. And at radio wavelengths, there is a lot of water that is detected in the atmosphere still, so you have to account for that. But if you're, for instance, in a location such as the Atacama Desert in Chile, where ALMA is located, or the SMA in Hawaii on Mauna Kea, the conditions are a lot better. So this part of the calibration is a lot easier.
So what did you discover?
So I have been a lot of the telescope data that I have used is to find proof that the chemistry across different stages, so for instance from molecular clouds to protostars to protoplanetary disks, is partially still connected, so that not all material that is initially formed is destroyed, but that some is still there, and then we can, for instance, use it to trace back the conditions under which it formed.
Trace back the conditions. So you wanna observe them on the different stages of evolution and to see if we can go back and see how did they start, right?
Yes. So one thing that I'm working a lot with are isotopologues of molecules. So my pet molecule is methanol, which is the simplest alcohol that you can form. And methanol is interesting because it has 4 hydrogen atoms, so it consists of CH3OH. And what can happen is that you switch out hydrogen for deuterium, which is heavier hydrogen, so you just add 1 neutron. And this process, which we refer to as deuteration, is mostly efficient at temperatures in molecular clouds. And it can't occur at warmer temperatures. So if you find a molecule that is deuterated beyond what is average in the ISM, you can assume that it formed under those cold conditions. So just to give like ballpark numbers, the ratio of atomic deuterium over hydrogen in the interstellar medium on average is 10 to the minus 5. But we find molecules that have ratios of deuterium over hydrogen on the orders of sometimes even 10 to the minus 1. So this deuteration process is very efficient at those cold temperatures. And if we find a molecule in a protoplanetary disk that has an isotopic ratio that is that high, then we can infer that it is formed already in the molecular cloud phase and that it is inherited. And because those ratios are so sensitive to temperature, but also like the density of the gas, for instance, we can then learn that at some point in that period of time, the system was in a temperature regime like this, for instance. And then we can also combine these observations with theoretical models, with chemical models where we have like a huge network of chemical reactions and where we look at many different molecules and can use the physical knowledge that we learned from observing the isotopic ratios to investigate a whole lot more molecules. And then we can see, oh, what other molecules should have formed at that point? What can we look for?
So you spoke about alcohol.
Yeah.
How surprising was that to discover this?
So it was maybe not surprising, but very exciting because methanol, for instance, which you should not drink that alcohol, by the way, that's super poisonous, but it is a very important ground base to make more complex molecules. So we found molecules with up to like 12 or 13 atoms in the interstellar medium. And like if you are a chemist, you will laugh at that a lot. But for us astrochemists, this is what we consider to be a very big molecule already.
Yeah.
And if you have like higher temperatures or also radiation from the star, you can split up methanol and into radicals, for instance. And it has been shown that either on the ices or in the gas phase, those radicals then continue to form more complex species, such as sugar-like molecules, for instance, that have
Do we have sugar in space?
Yes, we have sugar in space, yeah.
What else? What other molecules do we have?
We have, for instance, ethanol, so alcohol that you can actually drink.
Can we drink alcohol from space? That would be crazy.
Yeah, fun fact.
Yeah.
Fun fact. So another thing why we study the connection between prestellar cores or molecular clouds and protoplanetary disks is because we have comets in our solar system. And comets are believed to have formed in the outer protoplanetary disk where it was never that hot as close to the star. So comets are believed to be the most pristine material from the disk in which the planets such as Earth formed in the solar system that still have material. And we have actually found alcohols on those comets with an isotopic ratio that is related to what we find in molecular clouds and protostars.
In other protostars.
Yeah.
Amazing. So we kind of see that there are a few, like at this point of astronomy, we can observe star formation in a different stages, and we basically see that it kind of looks very similar, right? Like that other protoplanetary disks and other stars, they look like, of course, everywhere there's like a little bit of different conditions, so they ended up being a little bit different. But in general, it looks like physics looks the same more over everywhere.
Yes, yeah, we can say it like that, yeah. So the base ingredients for chemistry seems to be very similar in all star-forming regions, but then systems can evolve drastically different. So what we think is there's always some remnant material from the earliest phases that survives, but we have also a lot of evidence that once you have a protoplanetary disk, there are a lot of dynamical processes that happen that will destroy a part of those initial molecules and then also reform some of them. And it is a very intricate puzzle to try to
model that.
Yeah, to model that and find out what survives, what doesn't survive, and how much does the evolution of the system contribute to that. Because in an ideal scenario, we would love to have one model that explains all. But the better data we get, for instance, with telescopes like ARMA that have an amazing spatial resolution, they show us that the components in each system are so different that probably to understand each system very well, we need to model each of those.
That's crazy. So in order to like create a perfect model, there is no way at this point to create a perfect model of a star formation and how like the protoplanetary disk would look like.
This would be my take on it at the moment, yeah. Because as soon as we think our models are to par with the observational data, we get a better and a new generation of telescopes that reveal so much more that we didn't know, so we didn't ever consider it in our models, which is, I think, a very fun game to play.
Yeah, that's so interesting. So also the protoplanetary disks, they have a big impact on exoplanets, right? Do you also kind of see that in your data? Do you study that, or you just focus on the disks and molecules? Like, on which stadium are we talking about? Before planets are formed, or like simultaneously?
I mainly look at stages before planets form. I like to see myself as someone that studies the chemistry as it evolves and then basically gives people that look into the formation of planets an idea of what should be there. But also depending on how far away from the star you are, you will have a different chemical composition. Something that I haven't really talked about is that molecules can be formed in the gas, but also on dust grains in the ices of them. And depending on how warm it is, some molecules will be either in the gas or on the ice. So for instance, water will be on the ice if the temperature is below 100 Kelvin, but once the temperature hits 100 Kelvin, it will be in the gas phase. So depending where you form your planet in a protoplanetary disk, it will accrete water from the gas or not.
My next question would be, how many molecules do we have at this point discovered in space?
I think
what's the range?
about 350.
350. So a lot of completely separate molecules. Are they all molecules that we see in Earth, or is there something that we haven't seen in Earth?
As far as I know, don't quote me on that, I think every molecule that we've seen so far, we've also seen on Earth. Something that I should mention is that the astrochemist period table is a lot smaller than the ones that we usually learn in science class here. So the molecules that we look at mainly consist of carbon, hydrogen, oxygen, nitrogen.
How can you detect such a small thing, which is a molecule, that is so far away? Because we usually talk about, it's even hard to detect an exoplanet, right? And exoplanets are bigger than molecules. It is hard to detect sometimes so far away galaxies and stuff like that, and they are gigantic objects. What about a tiny molecule? Are we able to detect that?
Yeah, fortunately, there's not always only one molecule of that type there. There are many there, so that you can observe a large column of gas towards one object, and that gas then contains those molecules. And if there's enough of them, and we look at them with telescopes that are sensitive enough to pick that up, then we can observe them.
What if there is a mix?
So the nice thing is we can look at the spectra. So basically
Exactly. I think we should explain what is the spectrum, because that would be... So spectrum, but not in the sense of a visual light, but like also we can see it in the other wavelengths, like radio.
Exactly. So in the radio, for instance. So we can take a molecule, let's say, because I love it, and I worked a lot with it, methanol, and we can take it to a lab here on Earth and put it in a chamber and let it emit. And if we have an instrument at the same frequency as our telescope, we can use this instrument in the lab to pick up the signals of methanol. And this will give us the spectra, which means at every frequency where methanol emits, we will have a peak in the spectrum. And we can then use those reference spectra to look into space, and if we see methanol, for instance, towards a molecular cloud, and we see matching peaks of multiple lines of methanol in that spectra, and we can compare it with our reference spectra, we can say, there's methanol towards that molecular cloud.
So we basically can see a spectrum, which is like we see the... I don't know, maybe how to explain it, maybe space in a different wavelengths by wavelength by wavelength. And then we see some wavelengths where there's an emission, right?
Yes.
So these molecules are emitting some specific, very specific wavelength. So once we detect this specific wavelength in the specific region, we are able to see that these molecules are there. So it has to be enough of them there in order for us to be able to see this small detection.
Exactly, yeah. So I would never claim a detection of a molecule just based on one line, because sometimes there are other molecules close by. But if you have multiple lines of one molecule, then you can claim a detection. And also, the intensity of each spike of the molecule is dependent on the temperature as well. So there will be emission lines of one molecule that are brighter, let's say around 100 Kelvin, and then there are other lines that are brighter around, for instance, 10 Kelvin or maybe 1,000 Kelvin. So we can then use our knowledge that we gained from the analysis in a laboratory with some guesses about how warm it is in that system, what the density of the gas is, what the radiation there is, to match that, and then also get kind of a relation between the intensity of the different peaks that we observe and the frequencies that we detect. And if there is a good match, for instance, this also helps with being secure that all those peaks stem from the same molecule.
That's amazing. So tell me, what's the kind of the biggest question in your field? What's the most important thing you kind of focus on astrochemistry?
So personally, for me, it would be to find good tools to investigate the degrees of inheritance versus reprocessing during the star formation process.
What does it mean?
So basically, because we see, for instance, we have molecules in comets in our solar system that have those isotopic signatures that we find in molecular clouds around protostars. So we know that some of that material survived, but we don't know how much of it. And also, if we just look at the 8 planets that we have in our solar system and look at their composition and their size, they are vastly different, right? So there was a lot of different things that were going on. But yeah, so the biggest question for me would be to try to find different tools to analyze it. So not just look at isotopic measurements, but also get better models of the individual systems that we look at. So kind of get, even though I earlier said it is probably impossible to get like one generic model that fits all, but work towards that.
I see. So like to work towards that and see if there's like how close we can be to like be able to model that, and also go back in time and see if our solar system looked like that.
For instance,
in the beginning, right? That's amazing, and I would love to move on to next question, which is how is it to be a scientist? How is it for you to be a scientist?
It is really fun most of the time. I love doing research. I love to think about new ideas and projects, and also talk to collaborators and get new ideas. So that is a fun part. I also like to give talks about my research. We get the opportunity to travel a lot, partially to present our research, but also to meet collaborators, because no one can do it all alone. So we usually have bigger collaborations, especially when it comes to models that multiple groups use or improve, or also observational campaigns that usually involve more than one person. So it is great to get the opportunity to travel around, visit other institutes, go to conferences, go to see exotic places. So that is great.
Yeah, I would say that is a very fun part of our work, the travel part and meeting. And by that meeting, like completely different stories, completely different people, and learning their approach to science and get inspired by these people, right?
Yes, I totally agree. Yeah.
But also enjoying to do what we do, which is basically being creative and working towards new knowledge, right?
Yeah.
Okay, thank you so much. It was very nice to talk to you, and maybe hope to see you some other day on another episode. Thank you so much for listening. Today our guest was Beatrice Kulterer. Thank you for listening.
Thank you so much for the opportunity.